Okay. So yesterday we had just discussed about the first law of thermodynamics, which was applied for a cyclic process, isn't it? Now today we shall discuss the first law, which is applied for a non-cyclic processes. So as in case of yesterday, just a minute. Okay. So just in case of yesterday, we have discussed the first law, which is applied for a cyclic process. In order to say the cyclic integral of heat flows will be equal to cyclic integral of work flows, it has to be a cyclic process. So as in case of this, it might be any process which is cyclic in nature, which repeats by itself. So for all such cyclic processes, you can say by the first law that a cyclic integral of the heat flows is equal to the cyclic integral of the work flows for all cyclic processes. Now, today we'll be discussing the same thing, first law, when it is applied for a non-cyclic processes. Okay, when we apply the first law for a non-cyclic processes in the sense it could be just like this. Okay, it might be anything isothermal, polytropic, or adiabatic, any processes which is non-cyclic. If you apply a first law for such kind of processes, then the dq, the change in heat, will not be equal to the change in work. The change in heat will not be equal to the change in work, but the dq will be equal to change in internal energy plus change in work. Okay, so there is a new concept of the internal energy which comes out here when you apply the first law for a process apart from a cyclic process. When you apply just for a process, the internal energy will come into picture. Just a minute. Okay, so that is the thing which I was saying. When you apply for a cyclic process, the first law is applied as the cyclic integral of the dq would be equal to the cyclic integral of the workflows. Okay, when you apply the same thing for a non-cyclic process, then you would apply as dq is equals to dE plus deta flip. That means the change in the heat flow will not be equal to the change in the workflow, but in addition to that, there will be change in internal energy. So that is the concept of uh, the first law applied to a non-cyclic process. Now, what is this internal energy? We shall try to understand. Okay, this internal energy is nothing but a property of a system. It's a property of a system. See, every system has its own sort of internal energy in it.
Sir,
So, yes,
sir, screen isn't
yes,
visible.
Ashwita. Okay, screen is invisible. I think broadcasting has stopped. Okay, yeah. Now it's fine, I guess. Is the screen visible now?
Yes.
Okay. So I was discussing about the internal energies. So that is the thing which is separating the process from cyclic to the non-cyclic. So when you apply a first law for a non-cyclic process, the dE will come into picture. That is what I have said. The change in internal energy will come into picture. Now we shall discuss about internal energy, what it is and how it is. Okay. So internal energy is a property of a system. Okay. It's a property in the sense every system would have its own amount of internal energy in it. Okay. Second thing, it's a point function. Okay. It's a point function in the sense just a point on a graph, it's enough to evaluate its property. The whole path is not required to evaluate its property. So only a point in a PV diagram is more than sufficient to evaluate. So that's why it is a point function. Okay. And it is an exact differential. So all those things are there. So this particular thing, which is known as a point function and a property, so both resembles the same. If it is a property, it will be definitely a point function. So if it is not a property, then it will be a path function, as in case of your heat and work. So if it is a property, it does mandate that it should be a point function. So there is a question asked in your previous examination that describe energy as a property of a system. So you have to describe the energy as a property of a system. That means you have to prove that the internal energy or an energy is a point function and a property of a system. So there is some sort of theoretical analysis to it. We shall try to discuss it. Okay. Let us consider. Just interact with me while I'm doing it. So no need to write the notes, which will be provided to you. After you can update your notes from that particular PDF. Okay, just as in case of now, just try to concentrate. Okay, there are two states, state 1 and state 2 like this. Okay, these two states, number of different paths have been followed. So that means they initially from state 1 to state 2, it reaches through a path A. Okay, from state 1 to state 2, it reaches to a path A. But while coming back, it goes in a two different ways. That means the one is from path B, okay, that is from 2 to 1, I'm saying. From the 2 to 1, it goes from the path B. In the other case, it goes with the path C. It goes with the path C. So I can say 1A to B1 is one cyclic process. Okay, I'll just highlight it with this. Okay, this is one particular process, correct? One cyclic process, and other process is being 1A to C1. Okay, which is this. Okay, which is this. So in these two cyclic processes, I have to prove that in order to prove energy as a property of a system, I should prove that the energy, whatever energy I'm calculating at these two states, that is state 1 and state 2, are not dependent on whether you go from B or you go from C. Correct? So if you prove that it does not no matters that it go from B or C, the energy remains same, then you can naturally prove that energy is a property of a system and hence a point function. So in that sense, we shall apply the first law for this particular case here. The cyclic integral of d cube. Now I am choosing the first path, guys. Okay, for the first path, for this particular path, I am doing now. Okay, I am applying the first law. Okay, yes. So the cyclic integral of d cube is equals to cyclic integral of dw. This is what your first law says, is it? Now we shall apply this for uh, the first processes. I can say it as integration from 1a to 2a d cube plus integration from 2b to 1b d cube, that is equals to, that means integration from 1a to 2a, okay, and integration from 2b to 1b. Okay, it is coming back from in the path B. That's why it is B here. Similarly for the work now. Similarly for the work. So integration from 1a to 2a dw plus integration from 2b to 1b dw. So I'll take this particular equation as 1. Now same thing, I'll apply for the second cycle. Okay, I'll apply for the second cycle now. What it is, so applying the first law for the path 1a to c1, what it will lead. Okay, the entry level path is same, which is this 1 to 2 in the path A, that is same. So I'll take that. So 1a to 2a dkiv plus. Now, while coming back, it is not coming in the sense of P, but it is returning back through the path C in case of the second case. So that's why it is integration from 2C to 1C dk. Similarly, apply for the work also. So 1A to 2A dw plus integration from 2C to 1C dw. So equation 2. Now, what I'll be doing is equation 2 minus equation 1. So anything will cancel while I subtract equation 1 with equation 2. Any common terms there? LHS with LHS, I have to subtract this with this. I mean, this minus this, and this minus this. That is the approach. Anything would cancel? Yes.
DQ from 2A to 1A will cancel.
Yes, exactly. So what happens is, look at this term, integration from 1A to 2A dk, integration from 1A to 2A dk. So these two things will cancel, is it? So what would I remain is 2 minus 1, is it? So this minus this. So it is this particular term minus this particular term in your LHS. So let me write it. It is nothing but integration from, okay, 1A 1A, it is 2C, 1C dk, that is equal to integration from, in the RHS, which would cancel. Anything would cancel?
So A only will cancel.
Yeah.
The A term.
A term would go away. Generally, the C term would remain. So that is 2C dw. So this is your final equation here. Okay. Just a minute, I got a call. Okay. Okay. So where was I? Okay, so A term goes away, and I have left a term here. Okay, so this minus this, so it is dk minus of integration from 2b to 1b dk. Here it is integration from 2c to 1c dw minus integration from 2b to 1b dw.
The presentation is
Correct?
not visible.
Or presentation. Share screen. Okay. So when I subtract 2 to 2 with 1, you'll get this particular expression here. Now, what I will do is just reshuffle the terms here. Okay. What happens when I take the common integral? That means I want all b's on the one side and I want all c's on the one side. So in that case, when I reshuffle it, it would be 2c to 1c day cave, okay, minus taking this particular term to the either side. So it is minus integration 2c to 1c data play. Similarly, on the other side, it would be integration from 2b to 1b take care minus integration from 2b to 1b theta play. When you apply the common integral, you can just take it out. It is 2c to 1c d cube minus theta play. This is very important. Integration from 2b to 1b d cube minus theta play. Okay. From this, what I can conclude is, so dq minus dw is same for the process whether it goes from the path C or from the path B. You will be having the same amount of expressions inside it, correct? So whether you go from the path B or you go from the path C, the dq minus dw remains same for both the processes. Hence, it is not dependent on what path you take, but it is rather dependent on the end states, that is state 1 and state 2. So that's why the energy becomes a property of a system which is independent of its path but dependent on its point. So it becomes a property of a system and hence a point function. So that is a simple conclusion you can make from this. And how many of you know about different forms of energy? Different forms of energy. So basically, in the mechanics, there are two different forms of energy: kinetic and potential. What are this? Anyone else know? Because this is very
And
important.
kinetic energy is associated with the motion of object.
It is associated with the motion of the object. Very good.
Pot-
So, what is
Potential is a
potential
position,
energy?
position of an object.
Position of an object. So, how do I evaluate these things?
E is equal to mgh and kinetic energy is equal to half m square.
Excellent. So half mv square and this is mgh. Okay. Now, in thermodynamic analysis, what I'll be doing is, see, kinetic energy is half mv square. M is the mass, no problem. But what is V in thermodynamics? We have taken the letter or the alphabet V for the volume, is it? So again, if you take V here, it would be a problem. So rather, what I'll be doing is, I'll be taking the kinetic energy to be half mc square. Got the point? C is even the velocity. Okay. Why have done that? Because volume is represented by V. Again, it would be a confusion in the problem. So that's why I have taken half mc square. Similarly, for the potential energy, okay, for the potential energy, okay, so it is mgh, is it? So h is taken for enthalpy. Okay, h is already taken for enthalpy. So what I'll be doing, I'll be taking it as mgz. Okay, clear? So now we shall extract something. Okay, many are sending the messages regarding the TCS. We shall extract some of the energy forms and develop certain equation now. Okay. So we have learned that for the first law, it is dq is equals to du plus theta play. Correct? From the first law, it is dq is equals to du plus theta play. When you are applying it for a process, when you are applying it for a cyclic process, then it is the cyclic integral of dq will be equal to cyclic integral of dw. Okay. Now here it is for a process, it is dq is equals to du plus dw. Now this particular energy is, okay, the energy of a system can be summation of your internal energy, which is you, which is already present in the system, plus it can possess a kinetic energy, plus it can possess some of the potential if it is at a certain height. Okay, so these three different forms of energy can be found in a system. Number one is what? Number one is internal energy, which is represented by U. Number two is the kinetic energy, which is in the motion. Number three is potential energy if it is way ahead of a certain height. Okay, all these things are there. Now, differentiating the above expression, what you'll get is, so dE is equals to du plus dke plus dpe. Okay, so from this, I'll be just writing the things up. So it is dE is equal to, okay, dE is equal to du plus d of kinetic energy half mc square plus d is mg set. Okay, so now this is the actual change in the energy, the change in the energy, not only internal energy, but there is even all this. So it is the change in kinetic energy also, and the change in the potential energy also. So all these things has to be considered while you are deriving this particular thing, is it? Not only the internal energy, even the kinetic energy and the potential energy also changes. So considering even kinetic energies and potential energies. So what happens? dk is equals to dW. So first I'll be writing dW so that all energies are there on the one side, plus du plus d times of half mc square plus d times of mg set. Okay, now what do you mean by dkf? What do you mean by decay? It is nothing but the change is, suppose if there is a process from 1 to 2 which is going in this way. Okay. So what do you mean by decay? Decay was nothing but what is the change from here to here. Okay. What is the change from here to here? So how much amount of heat has been lost or how much amount of heat has been gained? That particular thing is nothing but your decay. So for that, since Q is a path function, can I just write it as Q 1 to 2 like this? Yeah? Can I do it? Yes or no? How many of you are listening or not listening? I don't know. Can I write like that?
Yes, sir.
Yes, sir.
Okay. Okay, good. So similarly, dW is nothing but the change in the work from state 1 to state 2. So since work is a path function, I can write it as W 1 to 2 like this. Okay. Now, can I write the same way as U 1 to 2 for DU? Can I write it? Can I write it U as U 1 to 2? Yes, can I write it? Not. If
No,
no, then why? Yes, Ashita.
it's a point function.
Exactly. Very good. So the DU, the internal energy, we have just proved in the previous theoretical considerations that the internal energy is a point function and a property of a system. That's why you cannot write it in that way. You can rather write it in U2 minus U1 because it is an exact differential. These two are inexact differential, depends upon the path of the system. And the internal energy being a point function and a property, it is an exact differential. That's why you can calculate it as a difference between the two states. This I have been mentioning since the first module itself. Okay, what do you mean by exact differential and what do you mean by inexact differential? And it goes similar in case of with the kinetic energy and the potential energies. Why? Because even that is an energy of a system as well. So I can just write it as taking the constants away half m. Okay, I can just write like this: m by 2 into, okay, it is c2 square minus c1 square plus, okay, plus Ranjit Acharya. Okay. Plus, now what are the constants here? M into G is a constant, and here it is Z2 minus Z1. So this particular expression is very, very important to be remembered, okay, which would help you in deriving SFEE, which is so damn important question. It has been repeated many, many times in your previous question papers. Okay, SFE is nothing but steady flow energy equation. So in order to derive that, all this which I have just derived are the prerequisites which is used to derive SFEE, which is known as the steady flow energy equation. Any doubts here in this particular concept of energy? Any doubts?
No, sir.
Okay.
No, sir.
Okay. So I thought of finishing SFE by today, but since many are not there, man, I'm not willing to do it. What shall we do? Okay, let me discuss some of the experiment, this thing, conditions. How many of you remember what is H? How many of you remember what is H?
Enthalpy.
Enthalpy. How many of you remember what is the expression for enthalpy? How would you calculate enthalpy?
U plus PV.
Excellent. So it is U plus PV. So enthalpy is nothing but the total heat content of the body. Heat content. I'm talking about the heat. So total heat content of the body is nothing but your enthalpy. Okay. And it is given by U plus PV. Kindly remember this. Okay. What shall we do now? Okay. So we shall discuss the heat flows of the various processes and close the today's thing. Okay. Now, listen, this is very important. I want everyone to answer. If you answer very fast, I can leave you in 5 minutes. Okay. Now, what is the first process? Isobaric. Okay. Which is constant here?
Pressure.
Which is constant? Pressure is constant. So what is the value of K here?
0.
Very good. So how does it look on a PV diagram?
Horizontal line.
How the work done from 1 to 2 is calculated?
P into V2 minus V1.
P into V2 minus V1, exactly correct. So if it is here 1 to 2, it is P into V2 minus V1. If it is from 3 to 4, it is P into V3 minus V4 as it goes. Okay. Now, so until here, you have learned from work and heat. From the first law, you will be understanding that, okay, what is heat flow from 1 to 2 if it is isobaric. Okay, for an isobaric process, the heat flow is always given by the difference in the enthalpy. Kindly remember this. That means it is H2 minus H1. Okay, for an isobaric process, the heat flow from 1 to 2, how it is given? It is given by the change in the enthalpy. How it is given? It is given by the change in the enthalpy, that is nothing but TH, that is nothing but H2 minus H1. Okay. Now, further you can note it as H2 minus H1 can be calculated as Cp into T2 minus T1. H2 minus H1 can be further calculated as Cp is equals to T2 minus T1. Okay. Next, which is the process?
Isochoric.
Second one is the isochoric. For this, which is constant? And what is the value of K for this?
Volume is constant and K is equal to infinity.
Infinite. How does it look on a PV diagram?
Vertical line.
So what is the work done here?
0.
So now the new concept of heat flow. So workflow you have just concentrated and learned about it. Now we shall learn how to calculate the isochoric heat flow from 1 to 2. And it is given by the change in the internal energy. How it is given? It is given as the change in internal energy, that is nothing but U2 minus U1. Kindly remember this. So U2 minus U1 can be further written as Cv into T2 minus T1. Okay, there it was Cp into T2 minus T1 because it is on constant pressure. Here it is Cv because it is constant volume. It is Cv into T2 minus T1. Now kindly remember, isobaric heat flow is given by change in enthalpy, whereas the isochoric heat flow is given by change in internal energy. Okay, clear with these two?
Yes.
Okay. The third process now, isothermal. So here the temperature is constant, the value of K. What is the value of K?
1.
1.
How does it look on a PV diagram?
The curve.
Curve.
A curve. Okay, so it is 1 to 2 like this. So the work done from 1 to 2 is a big circus in isothermal. Why? Because it has a multiple ways so that I can calculate my work done. Okay, just make a space for that. So what are the different forms? Number one is, yes, anyone would like to tell it? What are the different forms so that
P1
I can?
V1
Yes, P1 V1 into ln of
V2 by V1.
V2 by V1. So it is always V2 by V1, V1 by V2. So second form, directly you can write V1 into ln of, just ln of P1 by P2. And again it is given as in terms of P2 now. So P2 V2 into ln of V2 by V1, that is equal to P2 V2 into ln of P1 by P2. In terms of temperature, it is mRT into ln of V2 by V1 again, that is equal to mRT into ln of P1 by P2. So all these 6 forms of work done expressions are there. Now, what is the heat flow from 1 to 2, which is isothermal? So that is the question right now. From the first law, listen here. This is very interesting. dq is equals to du plus dw. Yes or no? Okay? dq is equals to du plus dw. Now, according to Joule, so Joule is a scientist, is it? So Joule is a scientist. What does he say is, this is very important, guys. Kindly concentrate. Okay. Your internal energy, is my screen visible? Yeah. No. So your internal energy is a function of temperature. Okay, is a function of temperature alone. What does it mean? According to Joule, Joule says that even it is proved, even in fact, it has a big sort of derivation which is not there for you. So kindly remember this. Internal energy is a function of temperature alone. What does it mean? What does it mean, guys? Any interpretation for this? That means, I would say here, so the internal energy is only dependent on temperature, nothing else. So it is only dependent on temperature alone. That means if you change the pressure, your internal energy will never change. If you change the density, your internal energy will never change. If you change the viscosity, your internal energy will never change. But if you change the temperature, only then your internal energy will vary. Clear with this concept?
So what about the volume, sir?
Volume also, none of the parameters will affect your internal energy. The only parameter which affects your internal energy is the temperature. That is what the statement given by Chow. Clear? So if you change the volume, if you change the mass, if you change any sort of parameter which you require, will never ever change the internal energy. The only thing which changes the internal energy is the temperature. So if you change the temperature, only then your internal energy would change. Got the concept?
Yes, sir.
Okay, now here's the important point. In an isothermal process, the temperature is constant. Yes? In an isothermal process, the temperature is constant. So if temperature is constant, what about it? The internal energy? Whether it would change?
It will be constant.
Exactly. So if the temperature in an isothermal process is something, but the temperature will be constant. If temperature is constant, automatically your internal energy is constant. Why? Because your internal energy is a function of temperature alone. Nothing else can change it except temperature. You're keeping that itself as a constant. So your internal energy would be constant. That means if your internal energy is constant, what about the change in internal energy? There would be no change. Yes or no? There would be no change in the sense the change in the internal energy would be directly zero. Got my point? Everyone. This is very important to understand. Okay? Abhinav,
Yes, sir.
got this? Why the internal energy is zero for isothermal process? Yes, Abhinav. Why it is zero for the change in the internal energy? Why it is zero for an isothermal process?
So, hello, sir.
Yes, Abhinav.
So, because temperature is constant,
Excellent. So temperature is constant. That's why your internal energy will not change. Then the change in the internal energy will become zero. Now see the magic. If the change in internal energy is zero, then what happens? Your dq is equal to dw. Yes or no? The dq will be straight away equal to dw. Then I can write it here. Q1 to 2 isothermal will be equal to W1 to 2 isothermal. That means if you calculate the work, that will be equal to the heat flow. That means again you can use all these same expressions for the calculation of heat flow as well. Okay, got my point. How you can calculate the isothermal work done? You can use the same expressions for the workflows, which is same for the heat flows, only in case of an isothermal process. This is very important. Okay, clear with this? Last two process will not take much time. Okay, clear?
Yes, sir.
Okay. And the fourth one, adiabatic. Let me go very fast now. Adiabatic is equal to here. Which one is constant? Entropy is constant. What is the value of K? K is equal to gamma, which is ratio of specific heats. Again, it is a curve on a PV diagram like this. Okay. Now, what is the work done from 1 to 2, which is adiabatic in nature? Simple, it is P1 V1 minus P2 V2 divided by gamma minus 1. And this is very interesting here. The adiabatic heat flow from 1 to 2. So what is a heat flow from 1 to 2? If it is an adiabatic, it is a big zero. So the heat flow in an adiabatic process is zero, and the workflow in an isochoric process is zero. Kindly make note of this. So the process in which the workflow is zero is isochoric, and the process in which the heat flow is zero is adiabatic. Okay. Now, the last one, the fifth one is the polytropic process. In the polytropic process, nothing is constant here, and the value of K is some arbitrary value which is equal to N. Again, it is a curve on a PV diagram. So work done from 1 to 2 is given by P1 V1 minus P2 V2 divided by N minus 1, and Q1 to 2, which is polytropic, is given as this particular expression here. This is very important. Kindly you have to remember this. Okay. And the derivations for all the heat flows. Now, let me finish up this. It is given by gamma minus N divided by gamma minus 1 into polytropic work. So that is the expression by which you can calculate your heat flow, which is polytropic. So gamma minus N divided by gamma minus 1 into polytropic work is nothing but this expression here. Okay, it is again P1 V1 minus P2 V2 divided by N minus 1. Okay, understood all the concepts? Yeah?
Yes, sir.
Any doubts in all this? So this is the basic structure of your thermodynamics. If you are perfect in this particular table, all your problems are damn easy. I'm sure about it. Any doubts here? So there is a derivation as we have derived the work done expression for all the processes, all the 5 processes. There are the derivations for the heat flow processes also. I think they have not been asked in an examination. That's why I have not touched it upon, but I have just listed out all the end results of the derivation, which is very important. Okay. Any doubts here? So
No, sir.
kindly take a
No, sir.
screenshot of this and write neatly in your notes. My handwriting is really worse. Sorry for that, but I think yours should be good. So write it very neatly in your notes. Okay, just take a screenshot and keep writing while I'm taking my attendance because this is very, very important. In the next class, we'll be deriving an expression which I've just stated in the middle of the class, which is known as SFEE, and it is a damn important question for your internals as well as for your externals also. So in the next class, we will pick up that particular thing. Okay. Now, Abdul Rahman.
Yes, sir.
Next is Abhinav.
Yes, sir.
Adarsh.
Present, sir.
Ashanul. Okay, one thing I just want to specify, man. I have rescheduled the class from yesterday's to today's. That's why automatically in your mail you'll be getting the recording of your previous thing. Okay, and please don't send me the requests for the access of that particular thing. Definitely, I'll be sharing all the things in a module-wise, arranged neatly in a form of a PDF, which has the links for every video. Beside that, you'll be having a topic. Beside that, you'll be having a link. So suppose if you want to refer any of the topic, you can just directly click on the link so that the video just pops out. Okay, I'm just planning for that. Once it is done, before your internals, I'll just put it on the Google Classroom. You can access from there. Okay. Next is Shalom Mustafa. Muhammad Reza.
Present, sir.
Akshay Arkotian.
Present, sir.
Yes, Lahari.
Present, sir.
Okay. Okay. Amrit. Amrit. Not there. Anvit.
Yes, sir.
Okay. Ashwin.
Present, sir.
Amrit is also there. Okay. Ashwin, yes, there. Ashwita.
Present, sir.
Benoy. Benoy. Fahad. Faizan.
Present, sir.
Gaurav.
Present, sir.
Gautam.
Sir.
Javel. Yam Karthik.
Sir, present.
Mohammed.
Karthik, present, sir.
Okay. Yes. Mohammed Fazil. Mohammed Sihab. Mohammed Tausif Ali. Was.
Present, sir.
Yan Suraj.
Present, sir.
Nafa. Anumita Nair.
Present, sir.
Okay. Nandish. Nartan. Okay, Nandish there. Nartan. Niharika.
Present.
Nishchit. Nitin George. Next is Omkar.
Present, sir.
Okay, Nishchit is there. Okay. Prarthan Jain.
Present, sir.
Pratish C. Suvarna. Prajat Mahabala Rai.
Present, sir.
Rakshan.
Present, sir.
Ramdas. Ramdas. Ranjat. Sabit.
Present, sir.
Sagar.
Present, sir.
Okay. Okay. Shahzad.
Present, sir.
Shashank.
Present, sir.
Shetty Sujay.
Present, sir.
Shetty Tejas.
Present, sir.
Shravan Kumar.
Present, sir.
Sriraj. Saurabha.
Present, sir.
Sumant.
Present, sir.
Varun. Okay, Sumant is there. Varun. Vigneshwara. Amit Sangoli.
Yes, sir.
Prajwal Hegde.
Sir,
Sandesh
Nilesh.
Shankar Patil.
Sir.
Nilesh, you have messaged me that you will be attending the webinar.
Sir.
Webinar got over, sir.
Acha,
It got over at
nice.
10:40.
Okay. Sandesh, Shankar, Rachan, Rohan,
Yes, sir.
Varun. Rohan. Okay. Varun, Adarsh,
Yes, sir.
Adarsh P.
Yes, sir.
Next is Muhammad Amin
Yes, sir.
and Numan Asaddi.
Present, sir.
Okay, guys, take care. So we shall meet in the next class where we'll be solving for the SFE. Okay. Have a nice day ahead.